Exponential functions. The general form of an exponential function is f of x equals a times b to the x power, where x is the variable, a and b are real number constants, a does not equal 0, x is a real number, b is greater than 0, and b does not equal 1. b is the base in the exponential expression and represents the growth rate for the function. If b is greater than 1, then the function shows exponential growth. If b is between 0 and 1, then the function shows exponential decay. Y equals 0 is the horizontal asymptote, and 0, a is the y-intercept. As with all functions, to find the y-intercept, let x equal 0. Evaluate f of x equals 2 times 5 to the x power. 5 to the third power is 125, times 2 is 250. F of 1.5 gives us 2 times 5 to the 1.5 power. That equals about 22.36. If we plug in negative 3 over 8 here for x, we get a solution that's about equal to 1.09. And here we have negative pi. 5 to the negative pi power times 2 is about 0.01. Find the exponential function whose graph is given below. As we can see, the y-intercept is 0, 2. That means that a equals 2. Compare the y-coordinates of your points to determine the base of the exponent. So 0, 2 then goes to 1, 6 right there. Therefore, b equals 3, because we had to multiply 2 times 3 to get 6. Therefore, y equals 2 times 3 to the x power. Find the exponential function whose graph is given below. The y-intercept right here is 0, 3, so a equals 3. Then we're going to compare y-coordinates. We go from negative 1, 12 to 0, 3 to 1, 0.75. In each of these cases, we multiply the y value by 1/4 to get to the next one. Therefore, b equals 1/4. So the equation for this exponential function is y equals 3 times 1/4 to the x power. Recall that transformations can also impact the graphs of exponential functions. The relationship between the general transformations formula and exponential functions with transformations are shown below. Here we have y equals a times f of x minus c plus d, and here we have y equals a times b to the x minus c power plus d. When performing transformations on exponential functions, the domain, range, y-intercept, and asymptote will change. When a horizontal shift occurs in an exponential function, there are two options that can be used for graphing the function. Number 1, using an initial set of points to perform the transformation. If we begin with this red graph here, we see f of x equals 3 to the x power. If we plug in various x values, we get those corresponding y values that map out this red line. Here's the transformation. G of x equals 3 to the x minus 2 power. You just plug in those same x values, but you'll get different y values. So as you can see, the y-intercept is now 0, 1 over 9 instead of 0, 1. So then you graph out the blue line, and you can see that there's been a horizontal shift right 2 units. The second method is to adjust the problem using the rules of exponents discussed earlier in this unit. So we have our original function here, the same as before, and now we have 3x minus 2 over here. We can break that up into 3 to the x times 3 to the negative 2, which gives us 1 over 9 times 3 to the x. So the a value has changed from 1 to 1 over 9. When comparing the points, the transformations can still be found. So once you've adjusted the problem using the rules of exponents, then you can just plug in x values and graph it out. And you can see the horizontal shift right 2 units. Now let's compare the domain, range, y-intercept, and asymptote in these two functions. Here we have f of x equals 3 to the x, and here are some points that are on that graph. Here we have g of x equals 3 to the x minus 2, which can be rewritten as 1 over 9 times 3 to the x, and here are some points on that graph. So the domain here for 3 to the x is all real numbers from negative infinity to positive infinity. The range is from 0 to infinity, since we have the asymptote at y equals 0, and the y-intercept right here is at 0, 1. Over here, the domain is still all real numbers from negative infinity to positive infinity. We still have that y equals 0 asymptote, so our range is from 0 to positive infinity, and our y-intercept is 0, 1 over 9. Compare the graph of g of x with the graph of f of x. Then compare the domain, range, y-intercept, and asymptote in these two functions. Here in red, we begin again with f of x equals 3 to the x. And here we have a transformation g of x, and that equals 3 to the x plus 1 power plus 2. You can rewrite this as 3 to the x times 3 to the 1, which 3 to the 1 is just 3. So 3 times 3 to the x plus 2. This is going to give us a horizontal translation to the left 1 unit, and then this plus 2 there is a vertical shift up 2 units. Here's all the information for f of x equals 3 to the x, with the domain of all real numbers, the range from 0 to positive infinity, the asymptote at y equals 0, and the y-intercept at 0, 1. Over here, with the transformations, the domain is still all real numbers. The range, however, has gone from 0 up to 2, so 2 to positive infinity, because that asymptote has been moved up 2 units to y equals 2. The y-intercept now is at 5 instead of 1, because we have an a value of 3, so the y-intercept would be at 0, 3. However, we also have this vertical shift up 2 units. 3 plus 2 gives us 5. The general form of an exponential function is f of x equals a times b to the x power plus d, where x is the variable, a and b are real number constants, a does not equal 0, x is a real number, b is greater than 0, and b does not equal 1. b is the base in the exponential expression and represents the growth rate for the function. If b is greater than 1, then the function shows exponential growth. If b is between 0 and 1, then the function shows exponential decay. Y equals d is the horizontal asymptote. 0, a plus d is the y-intercept. As with all functions, to find the y-intercept, you just let x equal 0. The general form of an exponential function with transformations is f of x equals a times b to the x power plus d. Sometimes you will see it in this form, f of x equals a times b to the x minus c power plus d, where the horizontal shift is visible. To rewrite the function without a horizontal shift, we can use the rules of exponents. If we begin with f of x equals a times b to the x minus c plus d, since b to the x minus c can be rewritten as b to the x times b to the negative c, we can then rewrite it with a positive exponent as b to the x over b to the c. F of x can then simplify to f of x equals a times b to the x over b to the c plus d. Then we can just move this b to the c over so that it's underneath the a. A over b to the c times b to the x plus d. Notice how we're almost in general exponential form with no horizontal shift. What does a over b to the c represent? The value of a over b to the c is simply a constant value, and thus can be represented by just a, as we do with our general exponential function. F of x equals a times b to the x plus d. Exponential functions can be used to calculate compound interest by the formula a equals p times 1 plus r over n to the nt power, where a is the total account balance, p is the principal or the starting balance, r is the annual interest rate, t is the number of years, and n is the number of times per year that the interest is compounded. Here's an example. Jaquan deposits $2,500 into a bank account that earns 8% annual interest when compounded monthly. How much money will Jaquan have in his account after 10 years? Here is our compounding interest equation. We have a principal of $2,500, a rate of 8%, which is 0.08. We're going to be compounding monthly, which is 12 times a year, so n is 12, and it's going to be 10 years, so t equals 10. We plug in all of the numbers, and we find that A, his account balance after 10 years, is $5,549.10.